All right. Good evening, everyone, and welcome to a new week of our classes. Um, we'll be continuing our discussion on memory and context management. Um, as usual, we start with a recap of what we had done earlier. So we will look at a recap of semantic memory, which was essentially the primary thing we covered last week. So who volunteer to give us a recap of what we talked about last week? I know that in the first class, I think almost all of us here were there, but the second class for the week, it was just the Olanrewaju, even though I believe that by now the video would have been online. So I would have expected that we had all watched it prior to this class. So who would help us with the recap of last week's content?
Sir, I want to try, sir.
Okay, please go ahead. Thank you.
We started with that's the part one, should I say, the segment of memory and context management in agents AI. I mean AI agents. It gave us a background understanding about the should I call limitation now of LLMs in that they don't understand text as it were, as in as text, as in ABC like that. Rather, they understand the numbers, which are vectors. And you said each word is converted into an array of numbers, which is called vectors. That's in the space, in vector space, and that these vectors, they are in the LLM's embedding layer. In other words, every word is vectorized through an embedding model and has a representation in the embedding layer. And you made us understand that these vectors, being array of numbers, they are, for instance, the good example of apple and banana, because they are both fruits, they are likely to be located in the same space, in the same vector space. That is, their distance, should I say the Euclidean distance now will not be far from each other. And there's a way of doing the calculation. You give us the formula cos theta, which is A dot B over AB magnitude. So it's a way of calculating the distance in the vector space. And you said if we have numbers that are, a vector that are close together, they form a cluster. Yeah, it's clustering. And that formula you give us is the cosine similarity, because it's cos theta, to find the cosine distance between two vectors in space. So from basic mathematics, we know that when the angle is when it tends to zero, then it means that they are very close. That's cos zero, I believe, is 1, correct? That means they are in the same, they have no distance between them, they are on the same plane, so to say. And you told us
Just if I may just come in here.
okay,
When the cosine similarity is 1, like you're right, cos 0 is 1, it just means that the vector directions, the two vectors have the same
the same.
direction. So
Okay.
I mean they are the same. Now, when they are in exactly opposite direction, that's 180 degrees of angle, the angle between them. Cos
Yes, sir.
180 is -1. So they are in opposite direction. When they are perpendicular, that's cos 90. It will be that should be a 0, if I remember right.
Yes,
So,
sir.
I mean,
Yes,
that concept of cos theta helps you to visualize the directionality, the relative directions of the two vectors. And so when they are in the same direction, they are exactly the same. When they're in opposite direction, I mean, one is in the negative or opposite of the other, and when they are perpendicular, it means they are just orthogonal. Um, yeah, that's and then when I was talking about embeddings, it was about I was trying to explain. We were already talking about vector-based semantic memory. So I was trying to explain the basis for vectors similarity and how that is used in vector-based um, memory. And yes, the the conversion of the tokens, the tokenization, converting the words into vectors, it happens at the embedding layer. You don't necessarily need to use an embedding model. I mean, the LLMs we have an embedding layer where that embedding is done, but there are also some models that essentially all they do is just to create an embedding of the text that's fed to them, and those are the embedding models. Just wanted to clarify that. Please go ahead.
Okay.
Elaborate.
Okay. Thank you, sir. Thank you, sir. So you went further to tell us another limitation of vector-only memory. I mean a limitation of vector-only memory, which is that they only capture similarity, but don't capture cognition. And you said cognition is the exact logic of the meaning. And I remember you gave the example of Father, if we talk about Abuja and Nigeria, we might find that they may be located in the same vector space or similar. Of course, we do expect the distance between Abuja and Lagos. I mean Abuja and Nigeria to be the same as, say, Nigeria and, say, pineapple, for instance. But then the fact that Nigeria and Abuja, for example, are close together, the similarity does not really capture the essence or the logic or the type of similarity that they may have. So okay, they are in the same area. So what type of similarity do they have? So the vector therapies only capture that they are related, but not the exact nature of that relationship. And that if we don't give this definition for that, it may lead to hallucination. That the closer distance is retrieved does not give us the entire fact or the correct fact of the matter. So there's likelihood of hallucination based on only vector-based memory in agents. And then it took us through some coding sessions. We went further to talk about knowledge graph memory in agentic AI, contrasting to vector-based memory. And the advantage of the knowledge graph memory addresses the limitation we identified with vector-based memory, which is that to prevent hallucination, um, the agent is grounded in a structured web of facts, such that if we are saying, okay, to give us an example of the citizen of contained in WorkSat, I picture it like maybe forming maybe a JSON object, or I don't want to say dictionary, such that things are mapped. So when they are retrieved, the nodes define the relationships properly in the knowledge graph. So there's no room for hallucination. And then it took us further through some coding session to explain, to where we are the demonstration of the concepts. That's the bit I can speak to, sir.
Okay, thank you very much for that. Still, if some clarifications, I'm taking a bit more time in the clarifications here because most persons missed the very last class. Yeah, vector based memory in vector space. Yeah, it can easily identify similarity between two entities, right? between two entities, so you can identify what they are similar or they are not similar, how similar they are, but it doesn't capture the exact relationship between them. For example, I know you mentioned orange and is it bananas? Yeah, it can, or even um, orange and lemon, for example. It can it can identify that they are similar, but what exactly is that relationship between them? It doesn't capture that. So that's where knowledge graphs come in, because knowledge graph it captures the relationship between two entities. Essentially, you have a subject, you have a predicate, which is a subject and an object, and you have a predicate, which is the relationship between the two entities, that subject and the object. And by capturing that level of detail, knowledge graphs help to reduce the propensity for hallucination, and as it provides better grounding of the LLM. Yeah, I guess that's the clarification I wanted to make. I will also ask whether anybody has any question at this point before we delve into what we have for today. I'm doing that because most persons here were not at the last class. Okay, so excuse me. Today we'll talk about episodic memory. Um, like we had mentioned, I think that was 2 weeks ago, or was it the first class of last week? Episodic memory captures the agent's experience, right? So it's like a chronological record of the experience that the agent has had. What exactly has happened as the agent has executed in the past. It captures a record of that chronologically. It provides continuity over multiple turns, right? So you've done first turn, the episodic memory where you implement it will keep a record of what happened in previous turns, thereby allowing the agent to use those previous occurrences in its execution as context for responding to future or context for its future actions or responding to future user queries. So it's based, it allows the agent to be able to figure out, hey, 3 hours ago, what did I say to the user? So if the user refers to some previous item in the conversation with the agent, the episodic memory allows the agent to be able to identify what exactly the user is referring to and use that as context as the conversation continues without having to ask clarifying questions and all that. Well, episodic memory, it captures its memory of episodes. Well, what exactly is an episode? One way of modeling an episode is the experience tuple, which comprises a state. The state here is the environmental context of the agent, the context before the current um, before the action that the agent is about to take. So let's say the agent execution is at a particular node. The execution cycle is at a particular node, say node A. Now, prior to getting to that node A, what is the environmental context of the agent? That is the state. The next is action. Well, in no particular order. Action here refers to what the agent does, the response it gives to the user, or maybe in a situation, if it's a tool node, that tool call that the agent makes. When I say the response that the agent provides, it may actually be, so if it's were just let's say tool call request that the LLM makes, that is the action. If it is the tool execution node that actually executes the tool, based on the LLMs to call requests. That is the action. Then there's the reward or result, as the case may be. Well, in a reinforcement learning context, in a reinforcement learning scenario, reward would be the more appropriate term. So essentially, what's the outcome of the agent's action, right? Assuming user provides the feedback, that is the reward, or what exactly? That's essentially the result of the action that the agent has taken, right? That's the reward or result, as case may be. And then based on that reward or result, what is the next state? Essentially, the next state is the state following the agent's action, because the agent's action typically will modify the state. So that modified state becomes the next state. And so with these four, you could model an episode. Of course, the experience tuple may also include additional elements like timestamps, like user IDs, like session tokens, and so on, depending on your specific use case and how exactly you built the agent. Are there any questions so far?
Yeah, I just want to say something, sir.
Right,
I was glad when you mentioned reinforcement learning. My mind was beginning to capture
when
that.
I mentioned what, please?
Reinforcement learning.
Oh, okay.
Because when I heard state, action, reward, my mind played on some things I've heard about. Though I've not learned, but I know that I learned that in reinforcement learning, the system is such that an agent. So is there a link between agentic AI and reinforcement learning directly, or because?
Well, there's actually a training technique called reinforcement learning. Some will say with human feedback, some will say from human feedback. So it's a way of let me just use this, a way of fine-tuning the agent to specific workflows or use cases, right? But apart from that, if you have an agent, like let's say an assistant, you can actually train that agent yourself, right? When the agent takes an action and you provide it with feedback on the action, right? I mean, you provide it with feedback to indicate whether the agent's action was satisfactory or otherwise. And depending on how that agent is built, the agent can actually can learn from those and store that knowledge, perhaps as in its procedural memory. That becomes reinforcement learning. So when it has learned from that episode based on your feedback, and that improves its performance in subsequent requests from you, you have the reinforcement learning has occurred because you provided some reward based on the agent's action, and he has learned how to or how not to carry out that kind of action, which should ideally reflect in subsequent interactions you have with it. Like, does that adequately answer your question on that, right?
Yes, sir. Just further clarification, sir. I understand that self-driving cars, I learned they work with reinforcement learning, because I know there is computer vision is there, but although I know I've asked this question before, though they may be agentic AI, but not based on LLM. Am I right, sir?
Well, they typically would use custom architectures. I mean, in terms of controlling the self-driving feature, was as an entire system. Well, a typical self-driving car today would also get to understand natural language. You can speak to it and all that. And I would assume that they've integrated LLMs to handle such aspects of the user's interaction with the car, but per the driving itself, no, that typically would not use LLMs. And of course, they have been working on those before LLMs became mainstream. So I don't think those use LLMs as yet driving technology.
Okay, sir. Thank you so much.
You're welcome. Any other question? Okay, so we'll go ahead. Now we'll talk about the types of semantic memory, starting with buffer memory. Buffer memory is essentially it captures the raw stream of episodes as the agent executes. It's working memory for the agent, right? So it captures the raw history. As the episodes occur in the agent execution, it captures that raw episode stream. Yeah, a literal transcript of recent exchanges is just essentially another way of saying that it captures a raw episode stream, and it's usually implemented using fixed length queues. I mean, you can leave it an infinitely infinitely growing buffer. I mean, at some point, the system resources will run out. So it's implemented using fixed length queues, and its advantage is that it preserves the exact nuance and conversational style of that interaction, because it captures everything raw, verbatim. But the downside is that it's expensive in terms of its token use. It's not token efficient because you're capturing everything, both the ones that are essential and the ones that are not very essential. Of course, it's limited by the context window because it has to fit into the context window. So it cannot grow beyond the context window. Any question? Okay, so we'll move ahead. Now we're going to look at some sample code to illustrate the buffer memory. I'll stop sharing for a bit, so then I'll share my ID. Was anybody able to set up the code that I shared in the Discord channel? No one. Okay, it's fine, but it's okay. But I would advise that you try to run it yourself after the class and modify the code and try out different options. That's one way of getting it at your fingertips. Okay, so I'll put for buffer memory and our demo code for buffer memory. Please give a thumbs up if you can see my screen. Okay, thank you, Adobe. Okay, thanks, Raju. I would assume that others can see my screen too. Essentially, these are the same things we've been importing so far. The only difference here is that I think it's the same thing, but we don't have anything new. Okay, and now we are going to use Neo4j as our graph database. Last week we used NetworkX to simulate the graph database. That's what we use for our knowledge graph. But today now we're using Neo4j, which is an actual graph database. And the configuration here is the same configuration that we've been using. Just find that we want to use growth models, loading the environment variables, defining the model, the LLMs, the embedding models, the Davili search tool, creating a vector store, and now creating a connection to the graph database, and now our state. The addition we have in the state from what we had last week is this chart history. This chart history forms our buffer memory. It essentially is a list of all the messages in the history of the conversation as the agent executes all the messages. And we are annotating it with the add operator such that if you remember when we started the class where we built our first or where we looked at our first LangGraph agent, I mentioned that in the nodes, well, we don't return the full state, we just return the update, right? Now, and when we looked at edgeless nodes, this was more explicit in that the command object had an update argument, but with our fixed edge graphs and our conditional edge graphs, we were returning just the incremental update to the state, and LangGraph handles that update. So to enable us do that here, we are annotating this chart history state, the chart history with the operator, the add operator. That way, once we output any message, it gets appended to the chart history. Now, help us classify intent. I think we had that. We had this in the last class code. Essentially, what this does is giving a string. It's I'm not sure we had this. Given a string, it just classifies its intent. Is it a factual? Does it have a factual theme? Is it is it let me not use theme because thematic is one of the classes. Is it talking about something factual or something thematic or something? A composite means factual and thematic. Factual is this. Nigeria is a country, that's a fact. But thematic, if it's talking about a concept, something that's not a simple statement of fact, something like a concept, so that becomes thematic. Here, the extract triples, I'm sure we had this in the code that code for demonstrating a knowledge graph memory. So this essentially extracts from a given text, is extract a subject, a predicate, and object, essentially the two entities and the relationship between them, which is what we store into what is saved in the graph database. Contextualized query. Here, what it does is based on the user query and the history, a given user query and the history, it tries to, if that query depends on context from the conversation history, it extracts that context and rephrases the query as a standalone where that context is now embedded, making it easier for the LLM to respond appropriately. So our nodes. The retrieval node is essentially the same node we had from last week, just at its beginning. Well, we begin here with episodic memory, but there's also a vector strand, which is essentially the same. But the episodic memory here, all it does is it just extracts based on the query and the contextualized query using a helper. Contextual query becomes the active query. Now, the class weights dictionary, it just maps the intent to a float. The essence of this is to enable us to calculate the alpha and to figure out which of the memories is more appropriate to use as context in addressing the user intent in responding to the user's query. We'll see where I think we also had that in the what do you call it, in the last class code. So essentially here, the only thing we are using the episodic memory for is to contextualize the query, right? It picks if there's any relevant context from the history, that is any context from the history that is useful for addressing the user's query. We use this contextualized query helper to provide that context, and that generates the query, which is our active query that the LLM now uses to generate the response. That's essentially what we're using the episodic memory for in this case. The vector and the graph memories it's essentially the same things we had from last week. And we calculate the alpha, class weights, and so on, just like we did in the code from the last class. And essentially what this does is that if it is if the query, if it's thematic, for example, then it prioritizes the knowledge graph. If it's factual, it prioritizes the vector-based memory. And if it's composite, it gives equal weight to both of these. This is assuming that, first of all, that there is relevant context to retrieve from these memories anyway, because if there's no relevant information in these memories, it doesn't really, that particular memory doesn't matter anyway in the process of trying to address the user's query. Conflict resolution, this is where what I just talked about now comes into play. Now here, it's essentially the prompt is saying compare the information from the vector and knowledge graph context, and are there any conflicts between them? If there are any conflicts, then it picks the next node becomes a researcher node where it searches for information from the web to help address that conflict. But if there's no conflicts, then it goes straight to the writer node and it generates a draft of the report based on the context that was retrieved from the memories, and of course, bearing in mind which of these memories it gives priority to based on the identified intent of the query. The researcher node, just as we've had, it just uses Tavili search to get information from the web. The only addition here is that if there's any conflicts, we are adding that the LLM should resolve that, we are adding that the search results should be tailored towards resolving that conflict. That's the only thing we are adding. But I think we also had that in the last class code. And the writer node generates the draft of the report. Okay. So here's where you have this bias instruction, which is saying if the alpha is less than 0, that is telling us that excuse me, the intent is factual. So it's saying prioritize factual connections, that's knowledge graph, over conceptual flow, that's vector context. But if it is 0.5, that means it's composite. Then it gives the two contexts, the graph and vector context, equal priority. And where it is greater than 0.5, that means it's thematic. So it prioritizes the vector context over the graph context. Yeah, and we after the draft is generated, the next node is the critique node, which essentially it's about performing some reflection. The agent evaluates that draft to see whether the prompt here is asking it to determine whether the draft accurately and completely answers the query. That's the user query. And then it's to outline any specific strengths or shortcomings of that draft, of course, from the point of view of the user query. Thirdly, it's taking into account the context retrieved from the semantic memory, that's from the vector and graph context. It is to determine whether it's necessary for the agent to perform further research to gather more information. This is supposed to determine whether the next node will be the research node where it tries to perform another website. If the information that it already has from those contexts is sufficient for writing a satisfactory, that's in the opinion of this node, if the information is sufficient for writing a satisfactory draft, then it won't search again. But if it's not sufficient, it means it should search for more information. And then the final thing is to determine whether is to try to suggest a search query that would retrieve more relevant information. This way, the agent is able to reflexively improve its draft where necessary. Of course, the response is a JSON that has these 4 keys, whether a Boolean to indicate whether the current draft is adequate. If the current draft is adequate, we just persist whatever necessary information from that draft into the semantic memory, and then I'll put the result to the user. But if it's not adequate, then depending on whether it's necessary to search again, if it's necessary to search again, it goes to the research node to try to get more information. If it's not necessary to search again, it just goes back to the writer node to write another draft, taking into account the critique that was generated. And so it tries to solve whatever issues are flagged in the critique in the new draft that it's writing. And then if it's doing a new search based on the value of this key, then it will use the new the new search query that the LLM is suggesting. Okay. Yeah. And then save memory nodes, which is where we go when the critique node has. One other thing which is we also looked at, if the LLM determines that the current draft is adequate, we go to save memory. However, even if the current draft is not adequate, but we have exceeded the specified maximum revisions, which is this is obtained from a config a value in that you set in the config. So if we have exceeded this maximum number of revisions, we still output that. This is important to avoid getting into an infinite loop. If you remember the best practices we talked about when we were talking about the routing function in conditional edges, we specify that you should specify a maximum iteration count. So that is what this is. And of course, we update the state. Okay, here, this is using an edgeless graph. So that's why we're returning command objects. And then the save memory node is where the whatever knowledge is extracted is persisted into semantic memory. And of course, the episodic memory is also updated. So essentially the same, the vector for the vector store, saving into the vector store is the same as what we had in the last class, the same logic. But for the knowledge graph, now it's been updated because here we are now using Neo4j in contrast to network X that we used in the last class code. And finally, we also update the episodic memory by we return the messages from the current interaction, which will be appended to the chat history. Now, for the execution, we'll build a graph, and then we build and compile the graph, and then we execute. Here, our query, the initial query is just how large is Nigeria, right? If I've already run this, so I already have some information persisted in the semantic memory. Well, in this case, it will be the knowledge graph, since for the vector-based memory, it's files, which would only last as long as the session is running. But if you had used a vector database like ChromaDB or Pinecone, it would still be a similar situation to what I have here using Neo4j. But once you've run it once, you see that it's there. Anyway, we'll see that when we run. And then it will be probably will be part of what we retrieved when we run the second iteration, where we ask a follow-up question, which is what colors are on its national flag. Now, the first episode was how large is Nigeria, right? If you're running this afresh, typically based on the how the agent is built, it will search for the answer on Tavili, and then it will persist that information in the memory. And then when you ask the second question, what colors are on its national flag? What does it represent? We don't really know. But because we have buffer memory, the agent is able to figure out that it here refers to Nigeria. And that's what happens when our contextualized query helper runs. It's able to figure out that prior to this episode, the user asked about Nigeria. Hence, that it refers to Nigeria. And so it will now use, the active query becomes something like, what are the colors of Nigeria's national flag, or something like that. And if it has that information in memory, it will use memory. But if it doesn't, it will perform a web search using Tavili for that information. So let's run the code. while the code is running, does anyone have any question? Okay, no question. Yeah. So in the first episode, excuse me, the query was how large is Nigeria? I mean, there's nothing to contextualize. There's even no history, first of all. So that's it. Context relevance score is there's no context. So I mean, so the relevance score will be 0, and there's no relevant memory. Of course, there's even no memory in the first place. Yeah. So it goes to Stavili and it searches how large is Nigeria. And it retrieves this information, and the writer writes a draft about Nigeria's size. The critique says that draft is fine. I mean, the draft says Nigeria covers an area of approximately this number of square kilometers, and it provides that same information in square miles, making it the 14th largest country in Africa and the 31st largest in the world. And it provides a list of references, which are the web sources for the information. And now it extracts the following relationships which are persisted into the knowledge graph memory. Excuse me. First is Nigeria, which is the subject. Relationship covers an area of object approximately this number of square kilometers. The next one is a relationship between Nigeria and its size, but now in miles. The next one is that Nigeria becomes the relationship 14th largest country in Africa. Nigeria is the 34th largest country in the world, and so on. Now, this is double. It says double helix sync completed. Double helix in the sense that there is the vector memory and there is the knowledge graph memory. So it's updated both, and then it prints out the final response. While this script is printing out, you could have it provide this response, this as an API response or whatever, as the case may be. Then in episode 2, what are the colors on its national flag? That's the original query. The contextual queries are what colors are on the national flag of Nigeria. So it has updated this to make it clearer for the LLM, enabling it to provide a better response to the user. And this is the context relevance score. Now, the relevance score is calculated to be 0.13. If you look at the script, you see the logic that's used to calculate that. But we had specified, I think this is below the threshold we have specified. So that's why it's saying no relevant memory found. So it's not going to use these memories. But if it was above, if the relevance score was above the threshold we specified in our config, then it's going to use this. But of course, the data, the information it retrieves from memory is just about the size of Nigeria, really. That really doesn't have much relevance to the query, which is the colors on the national flag of Nigeria. And so this logic in of context relevance score calculation and the threshold we specified is appropriate here. So it searches on Tavili and it retrieves the relevant information and writes a draft, which the critic node is satisfied with. Of course, it should be said national flag of Nigeria features 2 primary colors, green, white. Okay, green and white. These colors have specific meanings. Green represents this, white represents this. Yeah, so those are the colors on flag of Nigeria. And the memories, the double helix memory is updated. That means it updates the vector memory with this entire response, and then also updates the knowledge graph memory with the relationship that were extracted from that draft. And finally, it outputs the response to the user. Any question on this so far? Okay, so we'll go back to our slides, then I'll stop sharing a bit and we continue. Please let me know when you can see my screen.
It's visible now, sir.
Okay, thank you. Yeah, before this, we should talk about summary memory. Now, like I mentioned earlier, the buffer memory it's inefficient in its use of tokens, which could actually become a problem. I mean, if you're using either way, whether you're using a paid API or you're running local model, there's still some cost. And yeah, later we are also going to see that the more you flood your context, it also affects the quality of the LLM's response. So summary memory enables you to capture the history, the agent's history, while also making more efficient use of tokens. And so it's like a narrative memory. It doesn't capture the raw stream of episodes, but it's it paraphrases them, it summarizes them, and so it makes use of the compressor pattern. In this case, it uses a secondary LLM. In the code we will look at, we are using the same LLM anyway, but typically you may use a secondary LLM, maybe even a smaller one, as the case may be, to summarize that history. And this summary is typically incremental. You update the summary you specify an integer and throw number of turns, after which you update the summary. Yeah, you don't write the summary from scratch at times. I mean, you just incremental update to the summary. Now, the summary memory helps to preserve long range context. You can capture more. You can capture more in the sense of the period covered by the episodic memory if you're using summary memory, because you are using the available storage space more efficiently. But with a buffer memory, it fills up quickly, and so you are limited in how long your episodic memory will cover using buffer memory. Yeah, I've already mentioned that summary memory has high token efficiency, but it's lossy because you're summarizing. You could lose subtle details like jokes or the specific phrasing, and yeah, this may or may not be important based on your use case. So your use case determines what exactly will be the appropriate um, um, solution for your episodic memory between buffer and summary memories. Any question on summary memory?
Yes, sir. Please, I'm trying to strike the balance between buffer memory and summary memory. Summary I mean, as far as the preservation of long range context is concerned, because I expect that will make it more lousy as in having more tokens. Whereas here is doing a summary. I'm just trying
Buffer
to.
memory uses a lot of tokens. It uses much more tokens to capture the same information than summary memory. buffer memory uses more tokens to capture the same information than summary memory. However, buffer memory is more detailed. So the disadvantage of summary memory is that it's lossy, right? It does not capture nuances, subtle details, because it's a summary. When you summarize, you actually a summary. You're summarizing. You lose some information. That's the trade-off for using less storage space, right? Now, the preserving long-range context is the advantage of the token efficiency of summary memory because it requires less storage space to capture the same information. You have more space to store history over a longer period. If you're using buffer memory, for example, your buffer will fill up fast. And when your buffer fills up, you either stop if you either stop storing history or you eject the older um, episodes to make space for the newer episodes, right? So that's really okay. Let me use an analogy. You have a box, right? And you have loaves of bread. For you, how many loaves of bread can you store in that box? If you put the loaves of bread exactly as they are, the box will fill up quickly. But if the bread is like agege bread and you can compress it, right? You are now able to fit in more loaves of bread inside that same box. Summary memory is that one that the scenario where you're squeezing the loaves of bread, you're compressing them, so you're able to fit in more of the history, and so you're able to preserve it. It preserves a longer range of the context than buffer memory. Does
So that
that?
means it's more qualitative, sir.
I don't understand what you mean by qualitative.
As in maybe less hallucination since it has good content, more relevant,
Well,
unlike buffer.
it's not. It depends on the context, right? It could make for less hallucination. It could also make for more hallucination depending on the use case. The important thing is that summary memory can cover longer history. However, because it is lossy, it misses details that buffer memory will capture. So if those details are important, then your agent would not be able to have those details in its context. Yeah, I mean, it's a trade-off. How much history do you want to capture? The longer the history you want to capture, the more you need to compress to fit into the available memory space. But so you need to decide between the range of context you want to cover and the amount of detail you want to capture in your episodic memory. If you want to capture more detail, if you prioritize detail over um, range, then you have to use buffer memory. But if you prioritize history range over detail, then you use summary memory. It's a trade-off you have to figure out and make as you are designing your agent. Does
Thank you,
that
sir.
answer your question? Okay. Any other question? Okay, so we need to look at the demo code for this too. I'll stop sharing for a bit and share my IDE. Please let me know when you can see my screen.
Yeah, it's up now, sir.
Okay. So let me minimize this. The imports are essentially the same because we're just using. Okay, Samson, you want to ask a question?
Yeah, good evening, sir.
Good
Can you hear me,
evening.
sir?
Yes, loud and clear.
Yeah, so my question is, first of all, the reason why we are using Olama embedding and we have to run the Olama on on our background. So the reason why I'm asking is that why can't we use maybe, is it not possible for us to use maybe online or cloud embedding stuff, or must it
I'm
be
assuming you
Olama?
haven't watched. I'm assuming you haven't watched the video of the last class because
Yeah,
I addressed
I've not,
this
sir.
there. I addressed this there. We are using Grok, and Grok, as far as I know, doesn't have any embedding model. Nothing stops you
Any
from
embedding,
using.
okay.
It doesn't have Grok, as far as I know, doesn't have an embedding model. Nothing stops you from using
Okay, okay,
a cloud-based embedding model if you have one. But me, we already have Olama, we already have Grok. I'm trying to minimize the different.
okay.
So nothing stops you
Yeah,
from
I've
using
been
some
able
other
to
one.
run it locally. Yeah, I've been able to run locally. I just want to confirm the reason why you're using.
It's
So
just because
also the
Grok doesn't
second
have
one,
an embedding model, as far as I know, anyway.
okay. Uh Also the file that you pasted, because I couldn't differentiate between the three because the codes are kind of like similar. I don't even know because everything is just showing message or text. So I don't know. The first one, what's the name of the first one, the second one, and the third one you pasted? So because I just want to rename the files.
Well, whatever name you want to use, but one is about buffer memory, one is about summary memory. The one we had already looked at is demonstrating buffer memory. The one we are looking at now is demonstrating summary memory, and then the third one will demonstrate a hybrid tiered memory. If you look at the code, you figure
Okay,
out which is which because the
okay.
buffer
Possibly,
captures
sir. Okay.
the buffer captures the raw execution history. Summary summarizes the hybrid is a
Okay.
hybrid of the two.
Okay, no problem. I will just look at when you are reading this one, so I'll be able to figure it out. Thank you.
Okay, welcome. So we're essentially importing um, the same modules and so on, and the configuration is the same. Excuse me. Yeah, the change starts from here. We had chat history in demonstration of buffer memory, where we used a list of base charts. I think it was list of base chart objects. Just a moment. Yeah, list of base messages. Sorry, and we annotated this with the add operator so that to make it updatable by line graph. So, but here we are just capturing the summary. So a string, it's fine. Excuse me. A string is fine. Just a running summary of the previous messages. The classify intent helper and extract triples helper is essentially the same as we had for likewise the contextualized query helper. Retrieval node in this case, excuse me. Well, our contextualized query helper, the only difference between what it's here and in the code we ran previously in this class was that, where is that? This is using the summary. When we were working on the buffer memory, we had to create a string from the chat history list. But here, it's already a string, so we didn't go through that. We just used that summary as context and ask the LLM to contextualize write that to be a standalone query. Of course, integrating the context of the history summary. So our retrieval node is just the same. The episodic memory integration here retrieval is just about contextualizing the query. And for the semantic memory, the vector and the knowledge graphs is the same as we had. So nothing new there. Conflict resolution is essentially the same because we are resolving conflict only between the vector and knowledge graph context. Research node essentially the same. The only difference here is that instead of using excuse me, instead of using a list of messages, it's of in the chat history, that's the raw episodes stream, capturing it as our episodic memory. Here we are keeping a running summary. Yeah, critic node is still the same, where we have slight differences in our safe memory node. Excuse me. We are updating the update of the semantic memory is still the same. It's only in the episodic memory updates that there's some difference. Essentially, all we are saying is we have a prompt. We are using an LLM. That our same LLM. I mentioned that before. You could use a secondary LLM, which could be a smaller one for performing this summarization step. We're just asking the LLM to update the summary that we have by incorporating the information from the messages from the previous the current state, which had been updated from the previous node. And so it just performs well, this print statement is just to track it was the old summary length, was the new summary length, to know whether there's any change. And of course, it outputs and will print out the final report like we've been doing. Yeah, what are the queries that we're using? Here, the first episode, we're asking, what's your official language in Kenya? The next turn, we ask what currency is used there. Now, there can be anything, but because in the first turn, the agent had captured the context that this is asking about Kenya, here it will understand that there here refers to Kenya, which the user asked about in the first turn. And so it will contextualize the query to become something like what currency is used in Kenya or something similar. And so we run this. Excuse me. Okay. So first turn, our original query was what's the official language in Kenya? And well, the contextualized query is official language of Kenya. I guess it's trying to make it more token efficient. There's really no context, but it just summarized that from our contextualized query helper. It asks that same query using fewer tokens. Because since there's no context, the relevance score will be 0. So it goes to Tavili to search for the official language of Kenya, and it retrieves information here saying English and Swahili and so on. And the writer node generates the initial report, which the critic node says is okay. And so we update the memory, we update the vector memory with that draft, and then we update the relationships that were extracted from that draft, which is one, Kenya has official language, English. Kenya has official language, Swahili. English is a remnant of British colonial rule, and so on. English is considered prestigious. And then the old summary had 20 characters. The new summary now has 157 characters. I've updated the summary. And then it prints out the final draft. We go to the next turn. What currency is used there, which has been contextualized to be what is the currency of Kenya. It's able to figure out that there refers to Kenya. And since there has been no, it doesn't have any information in memory, any of the memory about the currency of Kenya. What it retrieved was about the official language, which is what, that this is from the vector store, right? It knows that the query is asking about Kenya. It sees that there's something about Kenya in the vector store. It retrieves that. But the information it retrieves about Kenya from the vector store has nothing to do with the currency of Kenya, which is what the question is. And so this is, I just want to point out, you can see that it sees similarity between what the user asked and this information in the vector store. And so it retrieves it. If we did not implement our relevance scoring logic here, and the LLM went to use this as context in response, it could hallucinate, could start answering about official language of Kenya. Meanwhile, the user asks about the currency. And it didn't retrieve anything from the knowledge graph. Let me check whether, well, I don't know. Let me see. Was there anything? Okay, it still retrieved from the knowledge graph, but I mean, the score is still low, but none of that has anything about currency. And so it goes back to Tavili search, and it returns information about Kenya's currency. It writes a draft, the critique okays that draft, and it persists the information in memory, including the relationship that you learned. It rewrote it updated the summary. Previously, it had 157 characters. Now it has 276 characters. Now, we could update our logic for summary for the summary by specifying a length, a max length for the summary. If we had done that, then this summary would not be growing by this fast when it's updated. But even as it is growing, the growth is much less than it would be if we were using buffer memory. And then finally we print out that final draft, which is what we have in our logic. Any question on this? Okay, if there's no question, I'll stop sharing a bit and we go back to the slide. Excuse me. Please let me know when you can see my slide. Okay. So let's now talk about hybrid approaches to episodic memory. I mentioned that you need to have, there's a trade-off between summary and buffer memories. While the buffer memory is detailed, because because of its inefficient use of tokens, it has a limit to how much of the history it can store. On the contrary, the summary memory is efficient in token use, and so it can capture a longer, longer history of the agent execution. However, it is not very detailed. And so that's the trade-off you need to make using either of them. But you could try to get the best of both worlds by adopting a hybrid approach, where you use both a summary and a buffer. In this case, you could say keep the last n is an integer. Let's say keep the last 5 messages raw, because those are the most recent messages. Usually, recent messages tend to have more relevance to the current in the current conversation, at the current point in the conversation. Recent history tends to have more relevance than very old history. So you could say keep the last 2, last 3, last 10 messages raw, that's in buffer memory. And then every other prior message, you summarize it. That way, you also are able to, you get the advantage of detail in the most recent history, and then you also capture long history, but you compress them to enable you make more efficient use of. So yes, this hybrid approach still is not as token efficient as using only summary memory. It's also not as detailed as using only buffer memory, but then it tries to, the idea is to capture a sweet spot between having adequate detail in your episodic memory, as well as capturing history a longer duration. So it's just like still a trade-off. Now, zonal memory, that's another approach. Here in zonal memory, you have your buffer, you capture just like in the summary plus buffer approach, you have total, and so this is the size of the buffer. So that number of messages captured in the buffer. When based on your threshold, when certain conditions are met, maybe when you have up to 5 messages, for example, in the buffer, it summarizes them and keeps them in the summary and clears the buffer. Maybe every 10 minutes, every 30 minutes, every 1 hour, as whatever the case may be, it extracts information, it extracts facts from that summary and persists them in vector storage. Now, vector storage, let's assume you're using a vector database, that will persist over multiple turns, multiple threads, and so on. And even if you shut down the agent and restart it, you still have that. So this is like trying to get the best of all the worlds. Of course, there are still trade-off. You don't have the entire history in the buffer. You have some summary, which is shorter term, but you also have longer term storage, which when you're able to extract. Who was it? Kenneth, I think that was you when I was asking you about the information, whether your use case, whether your agent should keep track of your favorite social media content or something, but you mentioned that you could also track. I think there was something you mentioned you could also track, and I was asking, since that what you're tracking, yes, it will be in your episodic memory, but since it's really a fact, wouldn't it be better to move that to semantic memory? So this zonal memory is really what I was talking about. Over the long term, you extract important facts from your episodic memory and you move those to semantic memory, because those are things that would be relevant, maybe have long-term relevance in the agent's performance, the agent carrying out his task. Any question? Okay, if there's no question, we move ahead. Memory decay. Now, if you keep, let me use the term, dumping information into memory, it doesn't matter whether you summarize or whatever. Memory is a finite resource. I mean, physically, that information you're storing is stored somewhere, and that infrastructure where you store that information is a finite resource. Apart from that, there's also the fact that some very, very old information can grow stale, right? For example, if your agent, for example, had captured Bill Clinton at some point as the president of the United States, would that context still be, how relevant would that information still be today if you're asking about the president of the United States, unless you're asking for so-and-so president or in so-and-so year? So at some of the information in your memory could actually become noise, and they could poison your context in that they could, if the information is stale and you capture that context from your memory and your agent acts based on that context, the agent's action, the agent's response would not be optimal. So such stale information could poison your context. And so that's why it's important, depending on your use case, to implement some memory decay feature. The strategy you could use for memory decay include temporal decay, where you create something like a half-life for stored episodes, so that every whatever the half-life you choose, every time interval that's your half-life, the half of your episodic memory cut by half. You trim off or you eject about the half of it, the older half or something. Or another way is recency bias, where you give higher weight to more recent episodes, and so they are giving more weight in the context, and so the agent prioritizes them when it's generating responses or taking actions. Yeah, there's also importance scoring, which I think we'll talk about it. Where you rank the information based on how relevant they are, right in the store anyway. So yeah, importance scoring. So for example, the user says hello. How important is that hello compared to an error as the agent executes? So if you grant both of them the same level of priority, and you're persisting hello, of what use is persisting hello for the agent to know that, for example, the user told me hello at so and so time? How relevant is that really? And so with importance scoring, you're able to increase the weight given to more relevant information, right? It could be how relevant this information are you assign more weight, or how frequently is this information encountered in the user's query? How frequently is it relevant to the user's query? You could assign such information more weight, or just like the example I started with, how relevant is it? How similar is it to the current task? You're assigning more weight. So the exact criteria or criterion you use really depends on your use case. Or you could use a combination of them, or even some other criterion that is not in the list I have here. Any question? Okay, no question. So we look at some demo code. I'm going to stop sharing for a little bit and then share my ID. Please let me know when you can see my screen.
It's up already.
Okay. Yeah. I think here it's still the same. We're importing essentially the same. I don't think there's any new imports here. The configuration is also the same as what we've had in the previous two um, demos, and the state just captures essentially what we have. We have a chart history. We have a history summary. So here we are using hybrid episodic memory, both buffer and summary. We have vector and knowledge graph. So hybrid semantic, hybrid episodic memory. The same helpers that we had previously. Now, the additional helpers we have here, evaluate importance. Here, we're using a secondary LLM. Well, you could use a secondary LLM, but we are using the same LLM in these scripts. We are using the same LLM for everything, but for these secondary tasks, you could use a secondary LLM, which would typically be cheaper compared to your primary LLM, which generates the user response and perhaps also critiques, performs the reflection loop. So our prompt is in the evaluate importance helper is just asking the LLM to rate how high the information in the text that input text, how it's just to rate how whether as in rate how much that text deserves long-term storage. So it's telling it to prioritize facts and names. And the rating it outputting a float between 0 and 1. So 1 means certainly this must be persistent. 0 means say you should not store this in long-term storage. And that's essentially what that helper is doing. And then we have a helper that is what this helper does, get and increment top key relationships, is when we query the graph database, it retrieves the top key relationship based on our specification of top key, well, the default of 3. So let's say we are using 3. It retrieves the top 3 relationships, top 3 based on weight, right? When we are storing to the graph database, we're also assigning a weight. And each time we retrieve that same relationship, that same triple of subject, predicate, object, we increment the weight. That's essentially what this does, such that the more frequently you access a given relationship in that graph database, the more each weight is increased and the more importance is assigned. Because really, I mean, if the thing gets multiple hits, it could imply that something important. Almost all the queries are hitting this particular relationship. So it's something important. That's essentially what that helper does. And so our retrieval node is essentially what we've had before. It integrates the episodic memory. Here, it uses the summary memory to contextualize but you could use okay. I think no. Our contextualized query is using both the summary and buffer memory, if I'm right. Yeah, it's using both. I guess I didn't update this year. Yeah, this should actually not just be a summary informed query because the context, you use both the summary and history context, but you could modify the logic in your own implementation. And so it's essentially the same. We retrieve the information from the memory and we calculate a relevant score. And if we have when we retrieve, we now go to check for conflicts between those contexts we retrieved, essentially between the vector and knowledge graph context. And this is in the conflict resolution node. And if there's no conflict, we go to the writer node to write a draft. But if there's conflict, then we go to the research node where we perform a Tavili search to try to retrieve information to resolve that conflict. The researcher node essentially just performs a search using the Tavili API. The writer node generates a draft report based on the context we retrieved, both from the memories and from the results of the Tavili search, as the case may be. And it writes that draft, and then it goes to the critique node, which evaluates the draft to figure out whether it answers, it provides an adequate response to the user query, or it's necessary to, if it doesn't, we need to rewrite the draft. And even when we want to rewrite, is it essential to perform another search on Tavili to get more information and so on? Just the same logic we've had. And then when the critique node is satisfied with the current version of the draft, or we have exceeded the maximum number of revisions as specified in the config, then we go to the save memory node and we persist. Now, the update we've made in the save memory node is that we don't just save everything. We check salience, right? If the importance score is above the salience threshold that we specified in the config, then we store, we persist that information in memory, both the vector store and as well as the triples, we persist them there. And then we also implement memory decay logic here. Over time, we reduce the weights of the relationships in the graph database by a factor of 0.5. So each time we run the same memory node, we across board, we take out 0.5 from the weights of the relationships in the graph database. And then if for relationships that the weight is below a certain specified threshold, we remove them from the graph database. That way, we prune stale relationship from the graph database, minimizing its rate of growth so that it doesn't keep growing unnecessarily, and we remove stale information from memory, reducing the likelihood of context poisoning. And of course, after updating the memory, we also output the final draft of the report. And then the queries we are running with here is, what is the capital of Ghana? Next turn, in what region of the country is it located? Now, based on the context of the episodic memory, the model in this turn 2 should be able to determine that each here refers to Ghana, right? So it's asking in what region of Ghana is the capital located, whatever the name of that capital is, which will be Accra, I believe. So when the contextualized query here should be something like, in what region of the country, okay, it will also figure that the country here refers to Ghana, and then it refers to Accra, which is the capital of Ghana. And then another related query, who is the CEO of Microsoft? This comes out of the blue, so you should go search for that. Even though I probably would have already some stored information about this in memory, but whether it has adequate weight to be considered relevant is what I can't say now. And then it asks, what is his or her country of citizenship? Now, who does his or her refer to? The CEO of Microsoft. It should figure this out from the episodic memory. Now we run the script. I just hope I've not exhausted my usage limits on Grok for the day. Okay, so turn 1, the same, what is the capital of Ghana? That's the same query that is being used. No memory found. And so it performs a tabuli search, which gets information that Accra is the capital of Ghana. It writes a draft, which is okayed by the critique node. It persists the information from, so you see salience, it says 0.9. That means it's very important information to store. So it persists the information in the memory and then applies the decay logic. And here it forgot 6 connections. I hope those are not the same 6 connections that, so 6 connections are removed from the graph database because their weights have gone below the specified threshold. The next turn, we ask, in what region of the country is it located? And here, the contextualized query becomes, what region of Ghana is Accra located in? So we figured that the country refers to Ghana, it refers to Accra. And so we got information from the vector and graph databases. And the relevance score is still lower than the specified threshold. So it still performs a tabuli search, goes through the whole process. The critique node okays the draft, and then it determines that the salience is high, 0.9, and so it persists that information. And then about 28 weak connections have been removed. It has pruned the graph, removing 28 weak connections. Some of these weak connections are really things that have been persisted from previous runs I had, all these different scripts. So they may not even be related to this, but essentially, I'm using the same storage for all of them. So it's removing those each time I run, but typically each of your workflows should have its own storage so that you don't go and affect another workflow in your trimming, in your pruning of your graph. Turn 3, who is the CEO of Microsoft? Well, the what is retrieving from vector context is about Ghana, which has no BNN at all, and no wonder the relevance score is so low, 0.05. So it searches, goes through the whole process, and then now the next one is what is his or her country of citizenship. Is able to figure out that his or her refers to Satya, Microsoft CEO, and it still goes through that whole process again, and then it finally outputs the response, including references as specified in the prompt for the writer node. Any question? Okay, so that's essentially what I have for you today. Since there's no question, does anybody have any comments? If there's none, then we'll just call it a night. But if there is a question or a comment, then we'll take that before we round off. Okay, then, ladies and gentlemen, I guess that's it for today. Please try to run the code yourself, not just running it. Try to go through the code. Try to modify the code. Try to try different iterations, ask different queries. Try to modify the logic to do different things. That way, you get to have this at your fingertips. Meanwhile, your stage 5 task has been uploaded, and I think the deadline is next week, Wednesday. And so it's good also you try to look at it, even though I think you may need the knowledge from the class we have on Thursday for some of the requirements in that task. So am I free to take my leave now, unless somebody has any question for me? Okay, so I'll take that to mean that yes. Okay, Samson, go ahead, please.
Yeah, so going through the tags, I noticed that you said we should submit collab. So I'm kind of like looking, will this work on collab based on all the things you asked us to set up? And will it work on collab? So that's my question.
What aspect of it has not been done on collab in the previous tasks?
Yeah, because I think it's more of this because I'm looking at all this Travali and this RIS CPU that you said we should set. Are we going to set everything up as well on collab, or yeah, you just have to just write the code and everything will work out?
Sorry,
So I'm
Tavali and
just
what? Tavali is you are calling an API.
API, yes.
You have done the previous tasks, have you?
Yes, I've done it.
If you've done up to stage 4 tasks, you've been calling APIs from collab.
Okay.
For
So also now
new
the
4J,
embedding. So the
yep,
embedding, are we still going to run our Llama locally and will it work with collab, or we don't have to do that?
you can still run Olama on collab. People have been doing that in their previous tasks. You can also use some other embedding model that from a cloud provider. You're not constrained to use Olama, but you can run Olama in collab
Okay.
if that's your preferred route.
Okay.
For
Okay, I'll try it.
new 4J, Aura DB allows you to use a cloud new 4J as a
Cloud.
cloud service,
Yeah.
so you can use that.
Okay.
All right.
Okay, thank you, sir.
Okay, you're welcome. All right. Does any other person have a question? Okay, so I guess that's it for today. Good night, everyone. See you on Thursday.
Nice, sir.